So, hello everyone. Thanks for joining. Today we'll talk about ZenFS, zones, and RocksDB. I'm Hans Holmberg. I'm a technologist at Western Digital Research. And one of my household chores as a family father is taking out the trash. And as I live on the 4th floor of an old building without an elevator, this is a royal pain. SSDs need to take out the garbage as well as part of their reclaim process, and it's equally painful for them. While it seems impossible for me to get away from taking out the trash at home, I believe we can do something to help the SSDs. So I've built ZnFS to show that garbage collection can be avoided for RocksDB workloads using zone storage. So that's what I'm going to talk about today. But first, let's take a step back and ask ourselves, why are we doing this? Well, it's all about data growth. And IDC expects that 103 whopping zettabytes of data will be generated worldwide by 2024. So we have an amazing data growth in a lot of different fields like IoT, analytics, video, virtualization, and databases. And how do we cope with this massive amount of data being generated each year? How do we scale? How do we use the hardware we have available today and the technology we have today and expand that and use that in the best way possible so we can continue supporting this data growth? So to answer that question, we first have to have a look at the hardware we have at hand today, and specifically SSDs. So let's look at the hardware first. What do we have to work with? Well, solid-state drives bundle tens to hundreds of NAND chips and an SSD controller together. And the SSD controller manages NAND chips characteristics and exposes that storage to a storage interface to the host or the server. And a NAND chip is composed of erase blocks consisting of many pages, and within each erase block, you can only write sequentially. Erase blocks must be erased before new writes, and you have a limited number of erases of an erase block. So when writing to the media, when writing to the chip that stores the data, you have to write sequentially. And you cannot overwrite any existing data, but you have to completely write the whole erase block and then evacuate any valid data before you can write to it again. And you don't want to do that too often because you have a limited number of erases of an erase block before it goes bad. So this is what an controller has to work with. And because the interface that is exposed to the host does not adhere to these characteristics, but exposes an LBA interface where you can update each logical block separately, the controller has to have a flash translation layer that maps the logical blocks written by the host, written and read by the host, onto physical blocks that's stored on the NAND media. So how does this work? Well, for conventional SSDs, this flash translation layer maps logical blocks to physical addresses in some way. It stores this translation layer on the flash and keeps it usually in memory as well to enable fast lookups. So if you look at the graph here on the right, you can see that file A, file B, file C, file D is written using a file system, and that is passed to the conventional SSD. But no knowledge of which file belongs to which block that's passed onto the block is available. No. So it's a very thin interface between a thin supply of information that comes from the host to the drive. So the drive only gets the logical blocks numbers from the file system, so it cannot separate the files themselves. So what happens is at the SSD is that it needs to put those logical blocks sequentially into its erase units. And these erase units are usually a collection of erase blocks. So as it doesn't know which block belongs to file A compared to file B to file C and file D and so on, all that data from these different files will be mixed into the erase units on the drive. This means that the different types of data gets co-located in the same erase units. And when a file gets deleted, the space occupied can't be reused without erasing an entire erase unit. So that means garbage collection is needed to evacuate still valid data from the erase unit. If you don't do that, data will be lost. So the drive needs to relocate the data belonging to the rest of the files if they're stored in the same erase unit as the erase unit needed to be reclaimed. So a controller would do this in a way something similar to this. The controller picks an erase unit to be evacuated, or one or many, in this case 2. And still valid data is then evacuated to another erase unit. And once an erase unit is evacuated, it can be erased and reused. And this garbage collection causes rewrites of user data. And this leads to something that is called write amplification. And that is defined as drive blocks written divided by host blocks written. So if the drive writes 4 times, if it relocates that data 3 times, we're going to get a write amplification of 4. So if it's relocated 3 times, after it's been written the first time, we get this write amplification of 4. If it doesn't need to do any relocation at all, if it doesn't need to do any garbage collection, the write amplification is 1, which is the best idea. And what is the problem with this? Well, it means more drive writes per user write. And this leads to shorter lifespan of the drive because there'll be more erase cycles on the flash blocks or flash erase units. And because the drive needs to do a lot more background work due to the garbage collection, we get decreased write performance. The drive will keep on doing writes in the background to relocate data, and that will impact the write performance seen by the host. And because we have a lot of work going on the drive, we are also going to get impact on the read performance, so read tail latencies and read throughput. So that's bad. And one can ask, is this a problem with real workloads? And when we started looking into good use cases that would benefit from zone storage about a year ago, we looked at the write amplification for a common workload. That was RocksDB. And we measured the on-disk write amplification. So the drive side write amplification, not the entire system, but then just how many times the drive had to relocate its data. And RocksDB is built to be flash friendly. All files are written to sequentially. And it's built with data structured organized in a logical merge structure. So it's supposed to be great for Flash, and it is, but we still get a write amplification of 4 on the drive when we measured it, which is quite a lot. But it also meant that we could do something to improve this. So, who likes to take out the garbage anyway? Can't we do better than that 4x write amplification for that particular workload? Well, now we can. Now we have an addition to the NVMe Express specification, and this introduces the zone storage module for NVMe. It does this by introducing a new namespace type called zone namespaces. And this exposes a set of zones of fixed size to be written sequentially and reset for new writes. And this matches the non-media characteristics very well. And this addition, this namespace type implements its own namespaces command set, which inherits the NVMe command set, extends it, and puts some restrictions on writes. So you have read, write, flush commands available as usual. Writes are restricted to be only sequential, and you need to reset zones before you can write them again. But writes, you can use the same write command, and reads work as before, or on conventional namespaces. And then you have some extensions. And this is done and optimized for SSDs. Because it adds a more efficient interface to the flash media by aligning better with the characteristics of the media, which improves system level performance. And if we take a deep dive into how things are organized on the drive for some namespaces and zones, zone states have different states. A zone has different states. So a zone can be empty, open, closed, read-only, or offline. And these states can be changed with zone management commands if you explicitly manage them. So you have zone management commands like open zone, close zone, finish zone, and reset zone. And each zone has a zone size and a zone capacity. And zone size is fixed. So this is the global size for the entire namespace for a zone. So this is the address space that a single zone occupies. While zone capacity is the writable area within a zone. So to start writing to a zone, you have to write at this zone start LBA. And this is a multiple of the zone size. So you start at that particular zone start LBA, and you can keep on writing until you reach the zone capacity. Then that zone is full. And to be able to write to that zone again, you will need to reset the zone and start all over again at the zone start LBA. And it's also important to know that the controller often has some active and open resources associated to a zone. So the controller may need a bit of buffering and other hardware resources per zone. These resources are not unlimited, which means that usually you can only write to a limited number of zones at the same time. So you have to keep that in mind. So what is this good for, this new interface? It adds all these new restrictions and you have to write in a new way. What is the gain? Well, ZNS enables smart data placement. And this smart data placement enables better media utilizations and lower write amplification. So how does it do that? So if you compare to how the conventional controller the data placements on the drive, it's very different. Since a zone namespace exposes zones that map very well to the erase units on the drive, the application can choose to segregate different files into different zones. That means that these files won't get mixed, and once a file is deleted, you can reclaim that space directly without moving out any data from any other file. So that means you get minimal garbage collection and lower write amplification as a result. And on a conventional SSD, there's usually a 7 to 28% of this storage capacity reserved for garbage collection purposes. There needs a bit of space to do the garbage collection efficiently. And there's no need to reserve over-provisioning media for this. So this can be given to the application to manage. And because the management, the system level management of the media is now more efficient, we can now enable QLC media where TLC has previously been used. So QLC generally has lower number of array cycles. So write amplification reducing the write amplification using some storage can enable the same use cases on TLC as on QLC. So we can make up for those the limited number of the lesser number of array cycles on QLC with this technology. And also reduces controller DRAM requirements on the drive, because the drive no longer needs to map every single LBA to a physical address. It's enough to just map an address in a zone to a erase unit on the drive. So there is a great saving in DRAM on the controller, so that can be made more efficient. So that's great. So what would be a good application that we could adopt? Because this needs application cooperation to work well. Well, we went looking for an application a year ago, as I mentioned earlier, and we found RocksDB, which is a great fit. So RocksDB is a widely used persistent key value store for fast storage environments. It's log structured and flash friendly. It has a clear separation of hot and cold data. So we could do really nice co-location of files if needed. So we could co-locate files that have similar lifespans into the same erase units to make use of the whole capacity of a zone. It is open source, so it's easy to hack. It's portable, can be used in many different environments, and it has a really active community, which means that it's up to date with the latest storage stack improvements. So it has support for asynchronous I/O. It has recently gotten support for I/O U-ring and so on, used in many places. And maybe the biggest advantage is that it has pluggable storage backends. So we could easily write a backend that would interface some storage. Great. But first, let's look at on these data structures. So the way RocksDB works is when it writes a key value pair, it first writes it to a write-ahead log to store it temporarily. And these write-ahead log files are very short-lived, very hot data. And it's also stored in memory, in a mem table. And that is flushed down to the drive as sorted string tables. And these sorted string tables are compacted into levels that are colder and colder, depending on the access pattern of these keys. This means that we have the write-ahead log files, and we have the SSD files, and the write-ahead log files are very hot, and the SSD files have a relative temperature to each other. It makes them easy to separate. So we have a really great data model here. We can actually predict how long a file is going to live. So that gives us a great opportunity to do real smart data placement. So we looked last year at this, and we built a prototype which we showed off at FMS, where we did file to zone mapping, straight file to zones. And then we started thinking about how real upstream support for zone storage would look like in RocksDB. So after the prototype, I sat down and thought about it and came up with ZenFS. And the goal of ZenFS is to do end-to-end ZNS integration, to add native support for ZNS as a RocksDB file system class, and use as much as possible of RocksDB data knowledge to do smart data placement. And we do this to minimize write amplification. We do this to avoid garbage collection, minimize wear, maximize write throughput, and improve write performance. And we also wanted to add this natively into RocksDB to minimize integration effort for users. So users of RocksDB should not have to care too much about that we're using ZenFS instead of a normal file system. So that's what we wanted to do. Also had some architecture considerations. So we wanted to maximize reuse of existing components and leverage the existing zone ecosystem. The zone storage support in the Linux kernel, in libraries and so on, has been out there for quite some time for shingle magnetic drives. And we want to reuse all of that goodness and just improve upon it, not reinvent the wheel. Also want to create complexity down to a minimum. ZnFS is not designed to be a general purpose file system or a general purpose flash translation layer. It's optimized for RocksDB, and it should just do what is absolutely necessary to get great performance. And add some flexibility in the right places. So not, at least on architecture level, tie it down to a specific IO path. So it should be easy to extend with another way to write to the disk. For example, use SPDK instead of going through the Linux kernel zone storage interfaces. And the algorithm should also be flexible or in a place in the architecture where it could be optimized. Right now, I have designed something that works well, but there's plenty of opportunity to, I think, to improve it and make it better. But not tie it down, hard code it to something very, very specific at the moment. So with those considerations in mind, we landed in this architecture. So looking at the diagram here on the right, you see that we have apps like dbbench, which is a workload generating tool that comes with RocksDB, or MySQL, or any other database that uses the RocksDB library. Interfaces RocksDB code, which is untouched. So the database engine is not changed at all. And we have ZnFS hooking in using something called a composite end. So RocksDB has this concept of environments. And these environments is we could call it an OS abstraction layer. So there's a Windows environment, there's a POSIX environment that supports BSD and Linux and so on. Recently there's been a change that allows just the file system part being swapped out in one of those environments. So what we do in ZnFS is that we replace the file system part of that POSIX environment and let the composite end put that together in an environment that RocksDB can use for reading, writing, and doing all the OS specific parts. And ZnFS then manages all the data files. So it manages storage and reads of the manifest, which is the RocksDB metadata file, the write ahead log, and the sorted strings tables. The only thing that's not stored on the only things that are not stored on the zone storage namespace or zone storage block device is log files and log files. And that's done out of convenience. Log files because these are files that ensures that the database is only accessed by those who should access it, and make sure that it can be indicated that it's used. And log files are used just to store log information. So currently, ZnFS does not implement support for the log files because that might as well stay in the local file system. And the log files are better stored in the local file system, so they're easy to access for debugging purposes. But there's nothing that prevents ZnFS from implementing support from storing log files or log files. It's not just done at the moment. Feedback on this would be great if someone would prefer that everything is stored on the zoned namespace. So if you look at underneath ZnFS, this yellow-orangey box, what does it interface? Well, for zone management, it uses libzbd, which is a thin library to do zone management operations. So libzbd is a very thin, just convenience library for using the Linux kernel IOCTLs. It converts between sectors and bytes and has easy access functions to send zone management commands like reset, finish, and open, and so on, and report zones. So it's just a really thin layer to access what's already available in the kernel. That could be lifted into ZnFS itself, but when we have support in a library that does exactly what we need, we might as well reuse that and not duplicate the code. So zone management operations are done in using libzbd, and data flows as normal preread, prewrite commands or calls to the kernel. So the data path is just raw block device writes and reads. And we've done this to minimize amount of external dependencies. So only libzbd for zone operations and only raw IO calls to the Linux kernel. And it's fairly streamlined to try to keep the code size down, so it would be easy to manage and understand. It's about 2,000 lines of code at the moment, so it should be reviewable in a very long day. And if we dig into the ZnFS on disk storage format, let's have a look at that. File data is stored in a set of extents, and extents are a contiguous part of the address space within a zone. So extents map to a single zone, but files can be split over zones, so files can have multiple extents, which allows files of arbitrary size. And files can share zones, which enables full zone capacity usage. So if we have a good way of co-locating data in these erase units on the drive, we can do so. ZnFS allows this and does it. And that's file data, and then we have some ZnFS metadata on the drive, which stores file and global file system metadata. And this is stored incrementally in a rolling log on the drive. And it occupies the first 3 zones. So we need at least 2 zones to securely roll from one zone to another when it's full. And right now I keep 1 extra zone in case one of these zones should wear out and go offline. So I have a spare zone. And how do we do allocation then? We don't do a simple mapping from file to zone. So we wanted to do something smarter, right? And we have these ZNS constraints to work with. Like you need to do sequential writes only, have to limit number of open zones, and valid data must be evacuated. We can reuse a zone. So if you can reuse a zone, we would have to move all data out that is still valid, or wait until all files have been deleted that occupy that zone. So garbage collection is an option here, but that leads to write amplification. So we rather not do that. So we have those constraints to work with, but we also get some help from RocksDB. And the biggest help we get is write lifetime hints. So RocksDB provides separation of these different file types and the expected lifetime in relation to each other. So we get, we can separate metadata, write ahead log and SSDs, and we get different lifetime hints for the SSD levels. That's great for being able to collocate data of the same lifetime. We also get file size hints, which RocksDB provides before starting writing a file. So we could use that. Don't do that in the moment, but we could use that to predict how much space that would be needed by a file. And most importantly, RocksDB supports append-only writes, which is great because we don't have to do any really smart copy and write logic in ZenFS. We can avoid that. So let's look at the extent allocator. So the ZNFS extent allocator works as follows. So when data is written, a zone is picked for a new extent when a file is first written to, or when there is no capacity left in the zone. And the picking scheme is like this. If there's space left in a zone, fill it with warmer data to maximize capacity usage. So we pick the first zone that fulfills the condition that the zone lifetime is greater than the file lifetime or is empty. And if the picked zone is empty, we assign the zone lifetime to the file lifetime. So if you've written a file already to a zone, we only allow warmer data to be stored in that to make sure that we don't prolong the life or we have to wait a long time to reclaim it. And files hold a write lock to the zone they're writing to. So we have one file per that's being written to a zone at the same time. So don't mix files together in a zone as they're written. And zones are marked as free when all files using the zone has been deleted. So we wait until all files that has been written to a zone has been deleted before we use it. So we don't do any garbage collection, no write amplification as a result. So you can say that ZnFS is very, very lazy because it just sits back and waits until RocksDB has deleted the file. So it waits until a file has been compacted and the data has been stored somewhere else, and waits for the RocksDB to delete it. And then when all files that have been written to a zone have been deleted, we can just reuse it. We also do something called fuzzy file size alignment. So the best capacity utilization is achieved if file sizes are aligned with zone capacity. So if we don't have to collocate data from different files, then in the same zone, that is the best solution, if we can do that. Because then we can directly reuse that zone when a single file is deleted. And target file size can be configured in RocksDB, but that seems to just to be a hint to RocksDB. It doesn't follow that exactly. So what we do in RocksDB is that we allow for approximate or fuzzy zone capacity alignment. So we set the target file size in the middle of the fuzz area, and then we finish zones when they have reached the fuzz area. So we allow files to vary about 10% in size. This is configurable. And when a zone is almost full, we finish it, which means we lose a little bit of capacity, but we also avoid different files being mixed together and the whole zone to be sort of held hostage for some extra time. So this means that, well, we get best capacity utilization if the files are exactly a multiple of zone capacity, but we can get great results if we allow for this sort of fuzzy method of aligning file sizes with zone capacity. So generally, when you try to reduce write amplification, you pay with space amplification. So if you do a lot of over provisioning, if you add a lot of extra space to handle the garbage collection, you can lower the write amplification on a normal drive as well. So if you just fill up a drive to half its capacity, you're going to get better write amplification. That's how it works. So the question here is, if you don't do any write amplification, or if you don't do any garbage collection at all for ZnFS, how much extra space do we need to do that? And we can't do perfect data placement because files do not add exactly up to zone sizes or zone capacities. So it's not perfect, but I've run here a workload that fills up the drive with a 100 gigabyte drive roughly with random inserts. You can see here as the sum of all files of RocksDB increases as we write more and more key value pairs. This utilization grows, and we also have a growing amount of space that can be reclaimed. So we need a bit of extra space to avoid garbage collection, but it's not much. In this case, it's about, I don't know, 16-17%, something like that. But considering that a drive normally reserves 7 to 28% of capacity for garbage collection, and still gets a write amplification of maybe from 2 to 4x, that's pretty good. So we can have a look at how this looks like if we visualize the write pattern on the drive. So here we have the tool LCBD viewer that comes with libcbd. And here we can see ZnFS writing to the disk. So every square here is a zone, and you can see how ZnFS writes to this zone sequentially. And you can see them being reused as files are being deleted. You can see here different compactions going on. And we just have to say that it's great this tool is great for understanding how zone storage works. So I can really recommend heading over to the libcbd GitHub page and downloading this and start playing with it in different scenarios. So ZnFS development, that's something that is ongoing at the moment. For debugging and testing, I use dbbench and dbstress. I've added upstream support for providing custom file systems to dbbench and dbstress as parameters. So you can run that with ZnFS. And GDB is great for debugging. I've used that when I really need to step through the code and understand what I've done. I'm a kernel guy, so I'm not very used to debugging with debuggers, but this works really well. So if you want to understand how things work internally in ZnFS, go and start ZnFS or one like dbbench with GDB and start stepping through the code. I've also added a good amount of tracing because understanding FTLs and file systems and things like that are almost impossible. It's almost impossible if you don't have any good tracing capability. So a ZnFS log file is generated for each run on debug builds. So that's stored per default in the temp directory. And it's called something like ZnFS block device name and then a time tag .log. This traces file operations, so when a file is open, when it's closed, when zones are allocated, and also displays statistics for zone allocations, so you can track disk usage, track how files are tagged with lifetime hints and so on. And this is great for debugging and evaluating extent allocation algorithms. So if you want to go and prove and do some research on this, it's fairly easy to do so. And what is the current state of development? Well, plumbing is done, working on evaluating it and tuning it and finish up the last things. I hope it won't be too long before we can push out a version 1 of this. There's already a request for comments out there. Sent the rest of comments, pull request sent out to the RocksDB repo. And then gathering input to make the version 1 available later this fall, hopefully. And it works with all zone block devices. So in addition to ZNS SSDs, it also supports SMR drives and emulation test devices such as null block. We also have a QEMU model if you want to simulate drives on PCI level, in case you don't have a zone block device, real zone block device drive available somewhere. And upstreaming is in progress, as I mentioned. All the preparatory work is now done. I've added support for custom file systems and made some bug fixes, so it should be good to go to add ZnFS as a file system in class implementation in RocksDB, but needs a bit of polishing. So please go and try it out. It is pretty easy to get started. Use memory-backed null block as its own block device, and off you go. Just use the latest kernel, and you get all the most recent additions to the kernel to support some block devices. Then you can instantiate a null block device that simulates a disk by storing things in DDR instead of on some media, and then you can run ZnFS on that. So if you want to try out the latest code with instructions, head over to the Western Digital RocksDB repo. It defaults to the ZnFS branch. So have a look at the README file, which I've patched with some instructions for how to get started with this. And if you want more information on the zones and the zone ecosystem, head over to zonestorage.io, where we collect information about some storage devices, about libraries, about emulation, and to have a sort of one-stop shop for all things. So with that, thanks everyone, and please provide feedback, code reviews, anything is appreciated. Thanks a lot.